Hello everyone and welcome to the Cálam Cymru revision sessions. The session this evening will focus on physics at AS level and will be presented by Mr James Wood from Cynvig Comprehensive School in Bridgend. The session will last 45 minutes where James will revise wave properties 3.2. If you have any questions during the session, please use the question and answer section and we'll do our best to answer your questions. You will see that there's a hyperlink in the Q&A section. Please leave your name and email if you are interested to receive more information on future events. Today's session will be recorded and the recording and any relevant resources will be uploaded to the e-sgol website under the Cálam Cymru tab. Thank you, James, and over to you.
Thank you, Jane. As mentioned, we are going to be going through wave properties today. I would recommend that if you haven't already done so, or if you need to brush up on waves, that you look at the previous video on waves, principles of waves, which will be on the Cálam Cymru website. With that in mind, then, we're going to make a start. So to begin with, here's the specification, the list of things you need to know. Diffraction occurring when waves encounter slits or obstacles. So one important thing to bear in mind is that waves have with them certain associated phenomena. And these phenomena are true and common for all waves. So whether we are discussing a water wave or a sound wave, a light wave, they will all diffract. It is a property of waves. It is a wave phenomena. So let's just discuss for a moment what diffraction is. Essentially, diffraction is the spreading of a wave when it encounters a boundary or a gap or an obstacle. So here, if you look at this first example here, we have a wave fronts coming towards a gap. When they hit that gap, they pass through the gap, but rather than just staying narrow in their focus, they actually spread out and emanate in all directions. Now, this principle has a sort of contingency. It is dependent on the relationship between the wavelength of a wave, and just to mark that on the diagram, if we're looking at these plane wavefronts, the wavelength of a wave is this distance here. The wavelength is indicated by the distance between those two lines, which incidentally, as indicated in the last video, correspond to the peaks of the wave. So what you're looking at here with these wavefronts, you're looking at peaks. So the wavelength is the distance between two peaks. And should it be the case that the wavelength, as in this first example here, is of a similar size to the gap itself, then we can expect a lot of diffraction. However, should it be the case that our wavelength, as is in this scenario here, the second scenario, if we have our wavelength which is far smaller than the gap, then we can expect a very small amount of diffraction there. All right. In this example here, now we have got an obstacle, and this could be, for example, anything, a mountain, a wall. Okay, depends what we're talking about. It could be sound, it could be radio waves. Doesn't matter if it's a wave. Then when they encounter an obstacle, far be it that rather than just cutting off at that point, they will spread out and curve around. All right. So that's essentially the basics of diffraction. Now, if you'll notice in the specification here, it does tell you as well a little bit about what you need to know. Sorry, back here. So the idea that there is little diffraction when theta is much smaller than the dimensions, or lambda, sorry, is much smaller than the dimension of the obstacle or slit. And then we've just covered this as well, the idea that if lambda is equal to or greater than the width of the slit, so equal to or greater than the width of the slit, waves will spread as roughly semicircular wavefronts. But if lambda is less than the slit width, the main beam spreads through less than 180 degrees. So really, we just covered those situations there. All right. A good application and a good way of maybe understanding this in action is to think about diffraction through a doorway. And let's imagine now that we have two people who cannot see each other, and maybe, I don't know, let's imagine that this guy is whistling a little tune. All right. You know, and I know that were that to be the case, that this person would in fact be quite easily heard by the person on the other side. So in other words, rather than just traveling through the gap in a narrow channel, the waves in fact would diffract through that gap and spread out. And as we've discussed previously, the reason why that would happen is because the sound waves are not exactly the same, but they're of a similar, or certainly parts of the sound are of a similar wavelength to that gap. And when I say similar, I'm talking about in the same ballpark in terms of maybe an order of magnitude or so. So that is why you can hear someone from coming around a corner, or you can hear someone maybe around the corner of a doorway. However, as you know, and as I know, with these people here, they couldn't see each other. Now, they might hear each other because of diffraction, but don't forget light travels as waves as well. Now, because light travels as waves, and because the wavelength of visible light is so short, the wavelength is so much smaller than this gap, okay? Wavelength is so much smaller than this gap, and in fact, it's smaller than the ratio I'm drawing it here, okay? That we would not expect to see any noticeable diffraction. And as such, you can hear someone around a corner, but you cannot see them around a corner because the wavelength of light is so much smaller than the width of the doorway, for example. And of course, to cause a noticeable diffraction with light, you have to have a very small wavelength, which we'll look at later on, because certainly that can be done, and it is entirely possible to diffract light. All right, so we're going to say that we have done that, we've done that, and that we've done that. We're making excellent progress already. All right, so next we're going to jump ahead. Actually, I put a little note there for me to cover this bit first. We're going to look at the principle of superposition, and we're going to give appropriate sketch graphs to illustrate what that really means. And I covered this briefly in the last video, but we're going to go through it quickly again now. So superposition means where two waves interact and the displacements of each wave are added together. So in the case of these two waves at the top here, which are in phase, so up here, you see these two waves are in phase, then what we can see is that the peaks here meet the peaks here, and the troughs meet the troughs. And as a consequence of that, those two displacements are going to add together to give us twice the displacement that we had before. Really simple. The peaks add to the peaks and the troughs add to the troughs. Now, we call that constructive interference, and then destructive interference down here, then you can see that where we've got the peak of wave 1 now, if it interacts with the trough of wave 2, then those two displacements are effectively going to cancel each other out. One is a positive displacement, the other is a negative displacement. They're going to cancel each other out. So the resultant displacement then is seen here. Okay, overall, we have zero displacement thereafter. So that is destructive interference, as the name implies, and essentially the waves cancel each other out. Okay, next then. So knowing that, we can start to explore now a two-source interference pattern. Now, if we have a little look at this video that we've got here, what I've got is two light sources which are coherent. In other words, have the same constant phase relationship, the same frequency, and the wavefronts are all lined up. More on that a little bit later on. Now, those two wave sources are going to produce identical waves. And as they interact, what we're going to find is that there are places where those waves will interact in such a way that we get constructive interference. And that constructive interference can be seen throughout the center here. And then there are regions where the waves are going to interact and we're going to have destructive interference. Now, the destructive interference you'll notice and you will see as the regions or the lines where there is no wave. Okay, now we're going to discuss why that happens, but we've already kind of made a start on that, because the destructive interference is where the peak of one wave meets the trough of another. All right, or if you like, one wave source, the wave from one wave source meets the peak meets the trough. That's fine, we'll do that for now. Okay, so I thought I'd just show you that, and we can label those points on here. Okay, so here, I didn't want to highlight this, sorry. So here you've got the constructive interference, and then maybe if I take a different color, and here immediately above that we've got the destructive interference. Okay, so that's from two sources. Now, the next part of the specification is the historical importance of Young's modulus. Young's experiments, Young's modulus, same guy, mind, but anyway, the historical importance of Young's experiment. I'm going to come back to that actually, and we're going to jump straight to G. Okay, we've done the superposition. We're going to jump to G, the path difference rules for constructive and destructive interference between waves from in-phase sources. Right. This is where this diagram is going to help, and this is probably the trickiest thing about interference patterns. So we witnessed here that we've got this interference pattern, and we're going to talk about for a second the phase relationship and the path difference and how they cause that to arise. Now, if we look at the center here, we can see that we've got a region here where two peaks, right? One from S1 and one from S2. Two peaks meet each other. And because the two peaks meet each other, as indicated by the lines, we're going to get constructive interference. But we also get constructive interference here, 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 here. And this is why, look, we get this bright patch, or this bright fringe, we call it, on a screen. All right. Now, the path difference, right, between S1 and S2, if you like, the distance that the wave travels from S1 and S2 to each of those points is identical. There is no path difference there. And what we'd say is that, if you like, the lambda, the path difference, path, oh, that doesn't say path. Path diff, if you like, equals 0, okay? And there's no phase angle between them either, all right? And we'll leave that there for now. We will also then think about explaining this bright fringe as well. And if we look at this bright fringe, then we can see a peak meets a peak here, a peak meets a peak here, peaks are meeting all the way where these lines intersect and cross, all right? But there's a very important distinction here, and that is that the light from S1, if I just draw this to here, okay, the light from S1 and the light from S2 travel different distances. But importantly, even though they travel different distances, the peaks will still be in phase. In other words, there'll be a peak from S1 and a peak from S2. Now, the difference here, or the path difference here now, for this to occur, must equal lambda, a whole wavelength, all right? It must be a whole wavelength for them to once again line up, all right? It's very important. Now, We can also then discuss the phase angle, and the phase angle will be the relationship between those two waves in terms of either, you know, pi, 2 pi, and so on. Now, because it's a whole wavelength, that's like one whole cycle. So the phase angle is going to be equal to one whole cycle, which is 2 pi. All right, one whole cycle, which is 2 pi. And now I think you might be able to see a pattern here, because we can look at where the peaks meet again here, and we get another bright fringe. And now we can think about what the path diff would be here. And that is going to be equal now, not just to 1 lambda, but 2 lambda. Okay, and the phase angle is now going to be equal to 2 complete cycles, if you like, or 2 complete waves. And therefore, that's going to be 4 pi. All right. Now, let's discuss the dark spots. All right. Now, the dark spots are just as important, and we need to be able to describe and then generalize as well what these distances are. So we'll take a blue for this. Now, I'm just going to pick this one here, not for any reason other than, well, it's not a bad place to start. Okay. Oops, excuse me. Oops, a daisy. Right. Oh, there we go. It's working. So if I take this spot here, this is created, this dark fringe, this dark spot is created by the peak of one wave meeting the trough of another. We've got destructive interference. We're going to be, if you like, in antiphase. And you can see that here, look. So here, in this point here, we've got the peak of the one wave in between 2 other waves, or 2 other peaks of the wave from S2. And therefore, where a peak meets a trough in the middle here, we end up with destructive interference. All right. Now, the destructive interference only happens when the wave or the path difference is now half a wavelength out of sync. Okay. And that half wavelength shift will cause a peak to meet a trough, and therefore cancel the wave out and produce that dark patch. Okay. Now the phase angle is equal to, you guessed it, just simply pi. All right, simply pi. And we'll do one more. We'll do one more for this one underneath. Now the path diff here is, again, it's going to be it's going to be some amount of wavelengths and a half. And in fact, if you think about it, it's going to be 1.5 wavelengths. It can't be a whole number of wavelengths because that would make it in phase. So it's got to be a whole number. Well, it's got to be a whole number plus half a wavelength, to put it in simple terms. Okay. Now the phase angle here, well, it was pi before, okay, and this is like 2 pi more than that now, because it's 3.5 wavelengths. So this is going to be 3 pi. All right. We can put all this together now and think about what we can say to generalize. Okay. So for, if you like, the dark fringes, all right, we have, if you like, the path diff is equal to, okay, n lambda by 2, where n is an odd number or non-odd integer. Okay. And then at the top here, we can say that for constructive interference, okay, so if you like, bright fringes, we can say that the path diff is equal to just simply n lambda. Okay, just n lambda. Again, where n is any number. Okay, n is any integer. And that is going to allow us to generalize for what these bright and dark fringes will be. So we said that this one here was, we said this one was 2 pi, 2 lambda. This one's going to be 3 lambda, and so on. Okay, the path difference has to be a whole number of wavelengths in order for us to have constructive interference. Okay, that was a big one, that was. So we'd already covered everything. The principle of superposition, sketch graphs, path difference rules for constructive and destructive interference between waves from in-phase sources, done. That was the last slide. And now the use of this formula here. All right, so this is from Young's double slit experiment. Now, Young's double slit experiment is a very famous experiment because, and we'll touch upon its significance now. Really, its historical significance. The nature of light was a difficult thing to understand. It's not an easy thing to measure. You know, you can see a water wave, can't you? Right? It's quite visible, but it's not obvious necessarily that light travels as waves in the same way. So Young's experiment proved that light could be diffracted, and it proved that light could be produce a diffraction pattern. And because diffraction is a wave-like phenomena, we were then able to classify waves, light as waves, which was quite a contentious issue because previously Newton had sort of suggested that light traveled as particles. I believe they're called corpuscles or something like that. I think it was. I'm trying to remember. Anyway, and he put that theory forward, and no one really knew the answer. Turns out that in the end, both of them were kind of right because of the wave-particle duality issue, which I'm sure you're all pretty much familiar with. Maybe you're doing it right now. I don't know. But truth is that waves can travel as particles and particles can travel as waves. Who knew? We're not meant to understand it. Why would we be? Anyway, I digress. Let's carry on. Young's double slit equation then. Lambda is equal to AY over D. It's just an expression to allow us to work out the wavelength of light given certain dimensions, which I've put on here. So D is obviously the distance from the screen to the slits. A is the distance between the slits. And then finally, delta Y is the separation of the fringes. And the separation of the fringes you can see at the top there. So, you know, given a past paper question, you might be given one of those or an unknown. One of the tricky things that pops up from time to time is measuring the fringe separation. So one of the measuring techniques that you need at A level, which is very important, is to do with measuring small things accurately. And in particular, in taking a larger measurement in order to derive and determine a smaller measurement. So what I'm saying is if you wanted this distance here and you had a ruler, you might well, measure this to be 4 millimeter, but because your ruler, okay, because of its precision of 1 millimeter, then you would be saying to yourself, okay, well, the uncertainty here in this measurement would be 1 over 4, which is equal to 25%. And that's not great, is it? That's quite a large degree of uncertainty in such a measurement. So an important measuring technique is to measure maybe the distance of many slits accurately and then divide by how many fringes you have to get one fringe separation. It's a bit like if I was to give you a textbook and I said to you, can you measure the width of a page? You can't do that with a ruler, okay, because every page is far less than 1 millimeter. However, if you can measure the width of the book, i.e. whatever it might be, 320 pages, then you can divide your measurement by 320 and get an estimate for how wide a page is. It's the same kind of principle here. And if this, I don't know, let's imagine this was 16, okay? And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that worked out nicely. 16 divided by 10 would give us 1.6. All right, so it's just a simple example of a measuring technique which you might be asked to employ in a past paper question to determine an accurate value for delta y up here. Right. Oops. Oh, that's strange. Anyway, moving on. We're going to now look at the next part of this, which is not, or if you like, moving things on from the double slit experiment, Young's double slit experiment, and looking at diffraction gratings. Now, this is very annoying. Now, you might have come across diffraction gratings already. This is the kind of one that I've used in my lab and that my students use. And when you pass light through a diffraction grating, much like with Young's double slit, you will be splitting that light up into bright fringes. You will be creating constructive and destructive interference, as you can see in these images below. You can use this again to determine the wavelength of the light source or the laser source that you're using. One of the things you need to do, though, is to be able to derive this formula up here. N lambda is equal to d sine theta. And we're going to give that a go now. Now, to derive it, this equation, it's all in the setup. If I'm honest, it's all in the drawing, like the drawing I've done here. So if we've got light hitting our diffraction grating, the diffraction grating, don't forget, is a series of many, many small slits, all right? And all those small slits are all going to produce a diffraction pattern, or they're all the light is going to diffract through all of them, and they're all going to add together to produce a diffraction pattern. That is why we get such a superior pattern, is because we've got so many sources. Anyway, if I consider this spot here, okay, if I consider this spot here, then I can start to think about the geometry of what would cause this first spot. So if we imagine this is my first order, or if you like, my first bright fringe, my laser's coming in, if you like, and pointing straight at like this point, and then my first bright spot is this one. We'd say that this is the order, okay? This would be n equals 1, all right? Now, to create this bright spot here, it must be the case that we've got constructive interference. Otherwise, you don't get a bright spot. Right, okay. So if this must be constructive interference, then it must be true, right? Just like it was before. If I call this S1 and I call this S2, then it must be the case that S2 minus S1 is equal to lambda. Now, the reason why that must be true is that the light from S2 must travel a whole number of wavelengths further than the light from S1 in order for those to arrive in phase at that point on the screen. And therefore, I know that this distance here must be lambda, because if I draw a little right angle triangle here, okay, then we can see that that extra distance that is traveled must be equal to lambda for there to be a bright spot. So I can label that as lambda. So now what I've done is I'm taking this triangle here and I'm extrapolating it out to here. I'm drawing the triangle again. And I'd recommend, if you were deriving this in the exam, you draw the triangle too. Now, the thing opposite here is going to be lambda, all right? And in this particular instance, it is absolutely just lambda because we're talking about the first order here. And then the other thing we're going to mark on here is the hypotenuse. Now, the hypotenuse is D, and D is the separation of the slits in the diffraction grating. And the angle then, the angle can be easily measured too. So I've got the angle here. If I measure the angle of this spot, right, up here from the central line, then I'm able, once I've got that angle, I've measured that angle, I'm able to actually derive this formula. So if then I look at just the trigonometry of this, then I can see that sine theta is equal to the opposite, which is here, over the hypotenuse. So sine theta is equal to the opposite, which is lambda, over the hypotenuse, which is d. And you can see it's starting to look like it now, okay? So if I then take d up, I end up with n, oh sorry, what I actually end up with for now, I end up with lambda is equal to d sine theta. Now, this is fine for the first order where n equals 1. But remember, we'll also get, okay, we'll also get the same effect up here, and we'll call this spot, or this order, this bright fringe, we'll call this n equals 2. This is the second order. Now, the important thing here with the second order is that that bright spot will occur when the path difference between S2 and S1 is now 2 lambda. So this is where the n lambda bit comes from. You can put any value in there, okay? So n would be, n equals 1 is the first order, n equals 2 is the second order, and all that's going to do is set that distance, the path difference, to a whole number of wavelengths, d sine theta. It is derived, we've done it, well done us, congratulations. Right, so let's move on. Double slit versus diffraction grating. A question quite often comes up, like, which is better for measuring the wavelength? I'm going to go through this real quick, look it up, it's not too hard. But diffraction grating is better. The slits, or sorry, the fringes are more clearly defined. They're not fuzzy like they are here. Okay, they're more clearly defined as a line. They are also brighter, so they're easier to see. And finally, they are more spread out. And because they're more spread out, they're actually easy to measure. But I'm not going to dwell on that because it's not too hard. Just need to look that one up, okay? But those are the three things. We're going to give that a tick. Yeah, okay, that's lovely. The idea that coherent sources are monochromatic with wave fronts continuous across the width of the beam, and when compared to more than one source, with a constant phase relationship. Right, so here's an example of what coherence means then, okay? So coherent light has the same wavelength, okay, same frequency, but if you look here, can you see all that the wave fronts are all lined up? In other words, the peaks are lined up, the peaks, and the troughs are lined up with the troughs. Here, we've got incoherent. Now, in fact, like the wavelength of all this light and the phase of all this, sorry, not the phase, the wavelength and the frequency is the same. It's monochromatic. However, if you look here, the peaks, like the wavefronts aren't lined up, so that's incoherent. Now, it's also true that another thing that will be incoherent is something like, I don't know, if you imagine a light bulb, okay, don't laugh, it's my light bulb, I'll do, okay. Now, a light bulb is putting out a whole spectrum of wavelengths, okay, a whole spectrum for wavelengths, so it can't possibly even come close to being coherent because there isn't a constant phase relationship. It's emitting light over the whole, or if you like, a large frequency spectrum, and you can only have a constant or interference pattern where you have a monochromatic source producing light of just one wavelength. Okay, right. So yeah, lasers coherent, an LED incoherent, and certainly a light bulb incoherent. The idea that two source interference to be observed, sorry, the idea that for two source interference to be observed, the sources must have a zero constant phase difference and have oscillations in the same direction. So again, we've sort of covered that, okay? It's really implying that zero or constant phase difference means that they are coherent waves, and that like with the laser, the peaks and the wavefronts are all in a line. Differences between stationary and progressive waves. How are we doing for time? 10 minutes, not bad. So stationary waves, these are produced from the superposition of two progressive waves of equal amplitude and frequency traveling in opposite directions. You may well have seen a demonstration of this. If you get a oscillator to vibrate a string, then if it's attached to both ends, then that string can be given a frequency such that it will produce a stationary wave. The wave travels from one end to the other end. It travels from one node to the other node, and then it reflects back. And in reflecting back, it starts to interfere with itself. The wave starts to superimpose with itself, the superposition of two progressive waves, okay, of equal amplitude and frequency traveling in opposite directions. And in doing so, you can actually set up certain, I guess you'd call them permitted frequencies. So if you like, this is the fundamental. And with the fundamental, what you can see here is that with this length that we have up the top, that the wavelength here of this in terms of L, all right, L is sort of equal to half a wavelength, isn't it? It's equal to lambda by 2. So therefore, lambda is equal to 2L. And then with the second one here, the wavelength of this, L, is just equal to lambda. Look, that's a whole wavelength. All this is just one wavelength, all right? This one, this third one, we've got, well, let's have a look here. That to there would be one whole wavelength, wouldn't it? So what we can see here is L itself actually contains, look, 1.5 or 3 lambda by 2. L contains 1.5 wavelengths, and therefore lambda is equal to 2L over 3, or 2/3 of the length, which makes sense as well, doesn't it? And then finally, L here, well, it contains 2 lambda, doesn't it? 2 wavelengths, 2 complete wavelengths, or lambda is equal to L by 2. So what that means, if you have something like a stringed instrument, okay, then when you pluck a string, like a guitar string, you will get mostly the fundamental, which will produce like the main body of the note. But within that, you get the harmonics, which we can see underneath. And those harmonics build up the richness of the sound and make it sound great. Okay, so the most expensive violins, like a Stradivarius, the finest violins ever made, will have just such a rich composition of all of these different stationary and standard waves, which themselves have their own unique wavelength when they vibrate, and in doing so will have a unique frequency as well. So the frequency, remember, C is equal to F lambda, so F is equal to C over lambda. The frequencies and therefore the pitches of all these sounds is given by all of the different wavelengths of sound that it can produce, given by these different stationary or standing waves. It's very interesting part of physics, actually, acoustics. I could talk about it for a long time, but not going to, other than just to mention that these are nodes, these are antinodes, okay? These are regions of maximum displacement. And you can see here, you can mark on the nodes and the antinodes, okay? Here and here. We can also as well start to look at what would happen to how stationary waves are set up in something like an open pipe, all right? So with an open pipe, which is like the brass section actually of an orchestra, what you have is a node in the center here for the fundamental, and then look, you have an antinode at either end. And as such, you can see that these here, whether it's a node at each end, like a stringed instrument, so this is your string section, right? Here is your brass section. Your stringed instruments and your brass instruments have a similar composition of harmonics, interestingly, all right? One's open at both ends. They have an antinode at both ends. One's, you know, if you like, has a node at each end, but they both have similar harmonics. However, quite interestingly, a closed shape, now you might guess what's the only one I haven't mentioned? That's right, it's the woodwind section of an orchestra. If you look at the way that these standing waves are composed, you can see that they have an entirely different set of harmonics, which is what makes an orchestra have its rich sound. Okay, so this is your oboes and your flutes and whatnot. Anyway, other things to mention about stationary waves then, just quickly, okay? One of the reasons I guess they call stationary waves is some points like the nodes will not move and they remain in that fixed position. Unlike a progressive wave, now every single part of a progressive wave oscillates with the amplitude. Okay, the full amplitude. Every single part oscillates with the full amplitude. However, what you get is a range of displacement. So the node, for example, has 0 displacement, whereas just adjacent to the nodes, we'll have a little bit more displacement up to the antinodes, which have maximum displacement, all right, or oscillate with the amplitude. Now, in addition to that, we can talk about the phase relationship either side of a node as well, because the parts of a wave either side, okay, i.e. here and here, they will be completely out of phase, or they will have a relationship of pi. So in other words, one's going up and one's going down, they're kind of doing this. So the particles immediately adjacent or either side, or the particles adjacent to nodes, the parts of the wave adjacent to nodes or either side of a node will oscillate out of phase. All right, and it's worth noting as well that the particles between nodes, okay, particles between nodes, all particles in here between these two nodes, they will oscillate in phase. So they are all completely in phase between nodes. And I think that is, just double check, difference between stationary and progressive waves. Now, I should mention as well, one of the differences, progressive waves, as I mentioned, will oscillate with a complete amplitude. Every part of it oscillates with a full amplitude, whereas in a stationary wave, there's a variation in the displacement of the particles in the waves throughout the wave. We also just discussed as well that there's a phase relationship between parts adjacent in either side of nodes and in between nodes. It's also worth mentioning as well that with stationary waves, they carry no energy, or they transfer no energy from place to place. So in the previous video, we talked about the idea that waves transfer energy from A to B. In this case, because that energy is reflected back, or because the wave is reflected back, there is no net transfer of energy as there is with progressive waves, because essentially it's a reflected wave. It's technically not 100% true, because if I pluck a guitar string, the energy is dissipated with time into the air and into the surroundings. But that's more to do with energy losses than energy being transferred from one spot to another. And the idea of stationary wave can be regarded as a superposition of two progressive waves of equal amplitude and frequency traveling in opposite directions, and the intermodal distance is lambda by 2. Intermodal distance lambda by 2. In other words, in between nodes, we've got this distance in between nodes is lambda by 2. Okay. And if I look at the time, I think that we are almost done. Yes. Sadly, there's no time for a past paper question, but I'll leave it up here just in case you want to pause it and give it a try yourself. So the first part of the question is all about Young's fringes and how they can be created using a laser beam and double slits. Then there's a little question which requires you to take a measurement of the bright fringes and explain what gives rise to the bright fringes and in relation to their phase and path difference. So maybe that's one you could try on your own. But that's time. Thank you very much, and I hope the session has been useful. Over to you.